condition, like remaining in excellent condition in a time period. So yeah, so this can be an example for a pavement deterioration, when with a high probability you remain in the state that you are now, and then with a low probability you will go to a worse state. And when you reach the worst state, you will remain there until you do a maintenance section. So we have a set of states. Usually for pavement, 8 states is considered. And then we also have a set of available actions. What we are really interested to know is that when we should do a specific action. Like if we are in state 7, what maintenance action should be performed? Should we do nothing, or should we do a routine maintenance just to lower the chance of going to a worse state? We also have the cost of performing each maintenance action in each state. And we also have the transition probabilities from the data. So we have this tool, Markov decision process, that can give us the optimal decision or optimal maintenance action in each state. We easily can use the transition matrix and cost function and get the optimal decisions from Markov decision process. Like here is an example of output of Markov decision process, which tells us that even if you are in the best action, like even if you are in the best state, like state 8, it's better to do a routine maintenance to lower the probability of going to the worst state. So what is the problem? The problem is that to calculate these transition probabilities, we are fixing the number of states. And we are also fixing the range of PCI in each state. Why it's not good? Because how do we know that PCI 91 is different from 90, and we are putting them in two separate states? And how do we know that PCI 19 acts the same as PCI like 95? So this is what we want to find. We want to, we basically want to not fix the number of states and not fixing the range of PCIs in each state, because the deterioration model that you fix and predetermine may be a suboptimal deterioration model, which would lead to suboptimal policies and then waste of resources. So basically, we want to find the optimal deterioration model, the inherent deterioration model. And because the data comes from the physics, the deterioration physics, if we only use the data and we don't make any assumptions, then we would get the inherent deterioration model, which is the optimal deterioration model. So how would we do that? So if we have a very large data set, maybe instead of assigning the PCIs to the states first and then finding the transition matrix, maybe we can find the 100 by 100 transition matrix first, and then use the Markov chain aggregation methods to find which PCIs should be aggregated together in a superstate. But to do this, we need a very large amount of data. So it's not really practical to find the 100 by 100 transition matrix. Maybe we can do something else. we can assume that data is generated from a hidden Markov model. And hidden Markov model is the same as Markov model, but the same as Markov chain. But the only thing is that the states are hidden. So you have a transition matrix which defines the probability of going to the next state, but you also have a emission matrix. For example, in the mood change model, uh, if so you don't know what is the mood of someone, but you know that if he is sad, he will drink espresso by 70% chance, and he will drink tea by 30% chance. So this is something that you observe. Although you don't know his mood, but based on this observation, you can make some guesses. So the states are hidden, but you have this observation. And there are algorithms that can give you, if you give them a path generated from a hidden Markov model, they give you the transition matrix and emission matrix for hidden Markov model. So here what we do is that to assume that the PCIs are generated from a hidden Markov model. So for example, we want to divide PCI into two states, a good condition and a bad condition. So we have the data, and we assume that it is generated from a hidden Markov model. So we can give it to the algorithms for hidden Markov model, and we also need to fix the number of states to be 2. And then we can get the emission probability from the hidden Markov model. And then from the emission probability, then we can say that PCI between 0 and 60 can be assumed as can be aggregated into a superstate, bad condition, and then PCIs between 60 to 100 can be also aggregated to the second state, the good condition. So we do this state assignment based on the emission probability that we get from the hidden Markov model. So here we are adding a level of flexibility. We still need to fix the number of states, but we don't fix the range of the PCIs in each state. But the thing is that we also don't know the number of states. Of course, we can use this hidden Markov model, and we can fix the number of states to be 2, 3, 4, 5, and then compare these. But there is a easier way also. We can let the data to talk for itself, and we can use infinite hidden Markov model in a state where we don't need to even fix the number of states. I will talk about the infinite hidden Markov model later. But what we get from infinite hidden Markov model is, again, the transition matrix and the emission matrix, which based on what we can find the number of states and the range of PCI in each state. So we wanted to find the potential benefit of using the inherent deterioration model, the model that is developed only based on the data without making any assumption. So we used the synthetic data. We generated data from a model, from a Markovian dynamic, which had 6 states. And also we generated data from a Markovian dynamic, which had 10 states. And then we used the data to find the standard 8x8 transition matrix that is usually used. And then we found the optimal policies for the predetermined model and the flexible model that is developed based on the infinite hidden Markov model. Yes. So we found that actually using the flexible model and finding the inherent deterioration model, we can significantly reduce the cost of the maintenance. Like this is the cost of maintenance during 25 years using the a standard 8x8 transition matrix, and also using the optimal model, which is based on data. And we can see that there is a significant cost saving. So we can use these non-parametric approaches to just use the data to find the model. And by doing that, we can make a more economically efficient planning. So here, I want to talk a little about infinite hidden Markov model. I start with mixtures model. Assume that you have data which you know that it is generated from a number of Gaussian distributions, for example. And you don't know how many Gaussian distributions. But if you fix the number of Gaussian distributions, you may underfit your model, maybe underfitting the data. Or it may be overfitting. So you can use infinite mixture models to let the data to say how many Gaussian distributions are there. And also, so the goal is to find this Gaussian distribution, find the mean and the standard deviation for them, and also find what is the probability that a single data point comes from a specific Gaussian distribution. Infinite hidden Markov model or hidden Markov model can be seen as a set of mixture models. Like each row of a transition matrix for each state can be seen as the mixing proportion. I said that here we want to find the probability that each data point comes from a specific Gaussian distribution. So this is what the transition matrix gives us. And also, when we go to the next state, then the observation comes from an emission distribution. So this is how we can see hidden Markov model as a mix of mixture model. So infinite hidden Markov model is basically an extension of infinite mixture model. And that's yes.
I was wondering apply this infinite mixture model for your cost model. Your application cost matrix. Did you use the infinite? I got the point of how you use the infinite mixture model to model deterioration. But when you report the cost, how do you calculate it? Do you have also a mixture model for cost?
So I didn't get your question. So we use the infinite hidden Markov model to find the number of states and also the range of the PCI in each state, right? And when we do that, when we find the range of PCIs in each state, then we can estimate the cost, right? Because we already have this. Okay, so we already have this standards cost for each state, right?
But it's only for 8 states.
Yes.
Can
So
you apply this for your infinite model? Because you have different ranges of PCI or states that you don't know the data give you. So you apply this.
Yes, we kind of use this cost. We actually use the weighted average to find the cost for the new estates.
Do you think it's possible to also look at the cost the way that you look at the PCI? Same way, so you can have consistency between two. Because using this aggregated cost model, it's just you have only 8 states and you apply to the infinite state. Just gets a very rough number. At the end, you're comparing that to a standard model. You see?
So here, like a state 8 is between 90 to 100, right? And a state 7 is between 80 to 90. So we come up with a new state which is 85 to 100, for example.
That cost should be different then.
Yes, so we use the weighted average to find the cost for that.
That's what I'm saying. Instead of that, would you mind, like, do you see any possibility to consider finding that the same way for the cost? I mean, that weighted average, something different.
Oh. No, because we don't have the detailed cost. Like, we don't know the cost for a specific PCIs. We only know this cost for the states. So this is the only data that we have. If we had more data, then we can.
If you go to the next slide, just all the way to the comparison between standard cost and the results.
I'm going
to go to the table that you show the cost and the results.
Oh, I'm sorry.
Okay, yeah. So that is standard cost versus the optimal cost that you're reporting. I bet like 80% difference. I don't know what's going to happen if you use different cost model for that. That's the thing. You might get even worse. I don't know.
Okay, that's something that you can look into.
And I also have one more question. How would you consider probabilistic hidden market model in this?
Probabilistic hidden market model.
Still, it's you're just playing with your states, not the transition probabilities.
Right.
How would you see that to consider probabilistically looking at the numbers, not just single transition number?
Oh, you're talking about the random transition. Actually, this is something that we are considering, right? Instead of having a specific transition matrix, yeah, this is something that is already done, and we want to add it to this also. Thanks. Yes.
I had a question about the optimization that you did here. What were your constraints? Were you just trying to minimize the cost? Or
yes, so we have a planning horizon which is 25 years, and then we also have an initial states, and we also have the transition probabilities and cost function, which is the cost for each action. And then we also have the user cost, like if you are in a bad state, like a state 1, when PCI is between 0 and 20, then the user cost is high. So we want to minimize the total cost.
Okay. And then did you have a minimum like PCI that you needed to get like maintained, or how like did you consider the performance of that?
I guess we had this constraint that at the end of the planning horizon, PCI should be greater than 450 something, I guess. So yes, if the planning horizon is 25 years, you can minimize the cost by having a really bad state at the end, because you don't care about what is it about the cost after the planning horizon. So we added this constraint that at the end of the planning horizon, the PCI should be at least 40 or 50, I don't remember exactly.
Okay. And then, sorry, one last question. So this is also the, I don't know if it was a network that you consider or just
no, it is for
a segment?
yeah, segment. Yeah, so the cost is $1 per yard per lane.
Okay. And then when you came up with the transition matrix, was that based on like a specific type of payment or just the entire network, or because it may change depending on?
Yes. So we assume that the transition metrics are for a specific class, like the type of payment should be fixed. We use the synthetic data here. We didn't use the payment data, but it should be for a specific type of payment for sure. Yes.
How much real data would you need to do the probability matrix in order to have a good model? Like, so you were talking, you did the synthetic data based on just the type of paving material. Like, if you go out and get asphalt data, like how many samples would you need?
I would say, assuming that PCI range is between 0 and 100, and we want the data to include all these PCIs, I would say at least something between 1,000 to 1,500, somewhere.
1,000, 1,500?
Observations, like.
Okay, transitions
Like over 2 years, the change.
Yes. So it depends how frequently the inspection.
They usually observe every year. You get one data point per year.
But but it's not only for segment. Like we have, if an agency does the inspection, it does it for all the segments, right? So there would be many segments, and even if each segment has like 10 observations, then we need like 100 segments, data from 100 segments.
But those segments, according to your model, are the same, are treated the same.
Yeah, they just need to be, I guess, from a specific type of pavement, right?
Yeah, but the segments may perform differently.
That's why the model is probabilistically. It's not deterministic. So it is assumed to account for these uncertainties. Yes.
Just to add to the number of states that you're assuming in here, in practical world, you may not be dealing with this many number of states. There are maybe 2, max 3 states the agencies usually consider or make a decision whether to do something or not. And this state would be at the state where the payment really fails, where they decide to do a reconstruction, or before it reaches to that point, whether to have a preventive type of a maintenance to really not to reach to that point. So there you may be actually living with only or 2 or 3 states at max. So you will never be finding a state agency, for example, or local agency doing something at the PCI levels at 85 or 95. And theoretically, yes, when you look at them, maybe there may be some recommendation, but in practical world, you may reduce the number of states.
Thanks for your comment. Actually, it's something that I didn't know because I only read the papers about this issue, and in those papers, they always assume 8 states for the pavement. So we got the idea from there. So we said, why 8 states? Why not 5? So
yeah, in practical, but in the practical world, especially for I mean, as far as we know from our state, how they make decisions, they sometimes even 2 states, I mean, they don't even consider preventive maintenance when the payment conditions are relatively fair.
But the beauty of this hidden market model is that you don't need to define the states. It just goes to the data and just it's not predefined number of states.
So
as you said.
Yes, so to find the transition matrix, first you need to define the states, right?
But that has to be defined by the agency has to make a
So,
decision
yes.
what to do with each stage, right? But the borders of the stages, I think, as far as I understand, they change.
Yes, this is what we want to say, that the border of the states and even the number of the states shouldn't be fixed. It should be something that the data tells us.
But the number of states in your work is fixed or not?
No, it's not. So I'm saying that, yes, this is what I'm saying. I'm saying that currently, in current practice, to find a transition matrix, first the number of states is fixed. But if we use this approach, we can just not fix the number of states.
All right. Any other questions? All right. In that case, let's give another one round of applause.